What if you had exactly $999 to build a small off-grid solar system? Could you build something that keeps your refrigerator running when the grid goes down? And more importantly, can that system actually recharge itself from solar? I'm Michael from Battery Hacker, and in this video, we're going to build a complete system around that $999 budget and then see what it can realistically power. Let's start with the basic components. For the battery, we're using a 12, 8-volt, 100 amp-hour lithium battery, priced at about $187. Next is a 2,000-watt inverter, which costs around $288. I'm choosing a properly listed inverter with built-in ground fault protection rather than going with the cheapest inverter available. For solar, we'll use 4 100-watt panels. That gives us 400 watts of solar power, with the panels connected in series. The 4 panels cost about $198. For the charge controller, we'll use a Victron 150/35 MPPT at around $165. Then we need the wiring and protection equipment. Solar cable comes to about $17, charge controller wiring about $14, and the battery cables around $31. Finally, we'll allow about $77 for the required fuses, breakers, and disconnects. Add everything together, and the system comes to roughly $977. That leaves us about $22 under our $999 budget. But here's the important question. What can this system actually run? Let's start with the battery, because the battery determines how much stored energy we have available when the sun isn't producing power. A 12, 8-volt battery rated at 100 amp-hours has a nominal energy capacity of 12.8 volts times 100 amp-hours equals 1,280 watt-hours. So, on paper, we have 1.28 kilowatt-hours of stored energy. Now let's use a refrigerator as our first example. Suppose the refrigerator averages 80 watts while its compressor is running, and its total daily energy consumption is about 640 watt-hours. If we simply divide the battery's 1,280 watt-hours by the refrigerator's 640 watt-hours per day, we get equals 2 days. So, the simple calculation gives us about 2 days of refrigerator runtime. But there's an important detail here. That calculation assumes we can use every watt-hour stored in the battery, and that the inverter is perfectly efficient. Neither assumption is realistic. The inverter consumes some energy while converting the battery's DC power into the AC power used by the refrigerator. For example, if we use 90% inverter efficiency, a 60-watt AC load actually requires about 60 divided by 0.9 equals 66.7 watts from the battery. So when we're estimating real-world runtime, we need to account for inverter losses instead of treating the battery's rated capacity as if every watt-hour reaches the appliance. And that's going to become especially important when we look at larger loads later in this system. But before we get there, we need to answer another big question. Can 400 watts of solar actually put enough energy back into this battery? That's where solar hours come into the calculation. And this is one of the most misunderstood parts of off-grid solar sizing. Let's look at that next. You might look outside and think, I get 5 or 6 hours of sunshine every day, so I have 5 or 6 hours of solar production. But that's not quite how solar calculations work. One peak sun hour represents the equivalent of receiving 1,000 watts per square meter of solar irradiance for 1 hour. In the real world, the sunlight level changes throughout the day. So instead of simply counting the hours that the sun is above the horizon, we use peak sun hours to estimate the amount of useful solar energy available. For our example, let's use 3 peak sun hours. We have 400 watts of solar panels, so our basic daily production estimate is 400 watts times 3 hours equals 1,200 watt-hours per day. That's enough energy, on paper, to replace the refrigerator's estimated 640 watt-hours of daily consumption and still leave some energy available for charging the battery. However, the 1,200 watt-hour number is a theoretical estimate. Solar panels don't operate at their rated output continuously, and there are also losses in the wiring, charge controller, battery charging process, and inverter. So I wouldn't design the system assuming you'll actually get 1,200 usable watt-hours every day. The good news is that the battery only contains 1,280 watt-hours. So with decent solar conditions, this 400-watt array has enough capacity to recharge the battery within roughly one good solar day. But what happens during winter? That's where location becomes very important. If your location only receives around 3 peak sun hours during the worst part of the year, your solar production will be much lower than it would be during summer. And if several cloudy days occur in a row, the battery may not fully recharge. That's one reason I always recommend looking at your worst solar month rather than designing the entire system around the best month of the year. Now let's move on to the wiring. We're connecting the 4 100-watt panels in series. The main advantage here is that series wiring increases the solar array voltage while keeping the current relatively low. Lower current means we can use smaller, less expensive cables and reduce voltage drop over a longer cable run. Let's assume each panel has an open circuit voltage of 22.7 volts. With 4 panels in series, 22.7 volts times 4 equals 90.8 volts. That's the maximum open circuit voltage under the stated conditions. But we shouldn't size the charge controller based only on that number. Cold temperatures can increase a solar panel's voltage, so we need a safety margin. Using a 1.25 safety factor, 90.8 volts times 1.25 equals 113.5 volts. So we need a charge controller with a maximum PV input voltage comfortably above that value. That's why a 150-volt MPPT charge controller is a suitable choice here. Now let's look at the charging current. The solar array is rated at 400 watts, and our battery is a 12.8-volt system. A simple estimate gives 400 watts divided by 12.8 volts equals 31.25 amps. So we're looking for a charge controller capable of handling at least that much charging current. A 35-amp MPPT charge controller gives us some headroom rather than operating right at its maximum rating all the time. That's also useful because equipment that constantly operates at its limit can run hotter, and excessive heat is something we want to avoid in an off-grid system. Next, we need to protect the wiring between the solar array and the charge controller. The exact cable size depends on the cable length, array current, installation method, and allowable voltage drop. For this example, a 12-gauge solar cable is appropriate for the expected current when the cable run is kept within a reasonable length. We also need a properly rated DC disconnect or breaker so the solar array can be isolated from the charge controller when servicing the system. And there's one important point here. The breaker is not there simply because we need something between the panels and the controller. Its rating has to match the actual array current, conductor rating, and the requirements of the equipment and installation. So don't automatically copy a breaker size from someone else's solar system without checking those details. Now we have the solar side of the system sized, but there's still a much bigger current flowing somewhere else. And that's on the battery to inverter side. Our inverter is rated at 2,000 watts, but because the inverter isn't 100% efficient, it will need more power from the battery. At 90% efficiency, 2,000 watts divided by 0.9 equals 2,222 watts. Now divide that by approximately 12 volts. 2,222 watts divided by 12 volts equals 185 amps. Adding a 1.25 safety factor gives us 185 amps times 1.25 equals 231 amps. So we're looking at a fuse around 250 amps, provided it matches the inverter manufacturer's requirements and the cable rating. For this current level, we're also dealing with very large battery cables, around 1/0 AWG or 50 square millimeters, depending on the installation. But here's the problem. Our 100 amp-hour battery has a 100 amp BMS. At roughly 12 volts, 100 amps times 12 volts equals 1,200 watts. So the battery cannot continuously supply enough current for the inverter's full 2,000 watt output. That's why the inverter being rated for 2,000 watts doesn't mean this particular battery can run a 2,000 watt load continuously. For something like a refrigerator, this can still work because the average load is much lower. And remember, refrigerators have compressor startup surges, so the inverter also needs enough surge capability. If you actually want to run large continuous loads, you would need more battery current capability, for example, another compatible battery in parallel, or a battery with a higher current BMS. That would, of course, increase the cost beyond our original $999 target. One more important point. The battery-to-inverter cable needs properly sized overcurrent protection installed close to the battery. And the cable size must match the actual installation and manufacturer's requirements. You may also see a small spark when connecting the inverter. That's normally caused by its internal capacitors charging, and a proper pre-charge method can reduce that spark. So, our final system is a 12, 8-volt, 100 amp-hour lithium battery, a 2,000 watt inverter, 400 watts of solar, and a 150-volt, 35 amp MPPT charge controller, plus the required cables and protection. The estimated total is about $977, keeping us under our $999 budget. This isn't designed to power an entire house. It's a small backup system for essential loads such as a refrigerator, lights, electronics, and other modest appliances. And that's the real lesson here. The inverter, battery, solar panels, charge controller, cables, and protection all have to be sized as one system. A 2,000 watt inverter is only as useful as the battery and wiring supporting it. I'm Michael from Battery Hacker. Thanks for watching, and I'll see you in the next one.